Right. Okay. So we've hopefully you've looked at the two previous videos. One is about the generic mass spectrometer, and the other one is about types of mass spectrometer that can be used in geological or geoscience kind of problems to create kind of appropriate data for different kinds of samples. Okay, so this this video will be about the kind of things we have to do with the data that we get out of the back end of these kind of analytical instruments. So I'm just going to share my PowerPoint presentation with you now. So what we're really looking for is next slide. Okay, is the thing that kind of the data we get will be in some kind of intensity of ion beam, maybe in counts per second, or kind of voltage or a current for each of the ion beams that we measure, for each element or isotope. And we want to turn that into some kind of concentration. Okay, and these are not the same things, so we need to do something to convert one between the other. And if we're just interested in measuring an isotope ratio, perhaps that's the thing that we want to measure, maybe the oxygen isotopes in our samples. The measured ratio of the intensity of different beams of different isotopes in the mass spectrometer will be related to the sample isotope ratio, but it won't actually be the same. Okay, so we need some way of either standardizing or correcting the measured ratio to the real isotope ratio. Okay, so this is kind of what we're looking at here. So I've just give me some pointers. Let's have a pen. So we might over time kind of measure a series of different samples with different intensities. Okay, and we want to convert those intensities into the concentration for each sample. Okay, so a relatively straightforward way of doing that is to take a series of standards that we know the concentration of. So maybe a standard here, here, and here. Okay, that we know the concentration of, that we know. So there's a graph of concentration that direction against the signal intensity in the up direction. Okay, and if we do that and we find out what intensity we get out of the machine for each different standard of different concentrations, we can create a line. This line here. I'll just give myself a laser point. So this line here, okay, which will enable us to take any signal intensity for an unknown. Okay, move across to here, and then we can work out what concentration that sample was. Okay, so there are some things that we need to consider when creating a calibration curve such as this, such as, for instance, when we get to very high concentrations, we might not continue to get a proportional response from our detector. It might just be that the signal intensity is so high it saturates the detector in the mass spectrometer, or it might be that the concentration is so high that there's so much dissolved salt in our solution that means that it inhibits the uptake of the sample into the mass spec. So we have this thing called the limit of linearity up here. So that's basically the range over which we can use a linear equation, y equals mx plus c, to describe the relationship between signal and concentration. Okay, so that's an important point. And then at the other end, we've got these things called the limit of detection and the limit of quantification. And I'll just go through and explain what those things are. So imagine if you were wanting to measure the concentration of cadmium in river water or something like that. Okay, before you actually put your samples in, you might want to just run some pure water with effectively no cadmium in it through the mass spectrometer and make a number of different measurements. Okay, so make a number of measurements of that, and that might be reflected by this black distribution here. So this is concentration loss increasing to the right. So we might get some low values for that, which could be a combination of actually some low level of contamination in the clean water, or it could be that this is just the background signal on our detectors in our mass spectrometer. So anyway, so this will have some mean value, and it'll also have some variance. Okay, so we could work out the standard deviation of the background kind of noise. Okay, now if we were to measure some samples that had very, very low concentrations, if we wanted to distinguish a sample from this distribution of basically the background noise, it would have to be at least 3 standard deviations away. So it would have to have a value of kind of up here. Okay, so if we had measured that sample a number of times, we might get a distribution, something looking like this. Okay, so if we made a measurement that was around here, we'd be able to detect that it was different from this distribution of the blank. Okay, but we wouldn't be able to really quantify how much is there. Okay, to really start to quantify, to put quantitative numbers on what the concentration is, we have to be at least 10 standard deviations of the blank. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 away. And once we get to concentrations that are high enough that way, then we can kind of start to say that that's an amount of for instance, cadmium in our river water samples that we can actually start to quantify how much is there, not that there's just some present. Okay, so just to go back, this range in between the limit that we can quantify and the limit of linearity for any one particular instrument or measurement routine technique defines the dynamic range of the technique. So this is the range of concentrations over which a particular technique is useful. Okay, and this is quite important because for techniques like mass spectrometers, this tends to be quite a large range. So we can use this one technique to measure a big range of concentrations of samples, whereas other techniques that for instance, photospectroscopy or something like that, might have a slightly smaller dynamic range. So we might, if we have very, very high concentration samples, we might have to dilute them down so they're all in a similar range so we can measure them and then account for that dilution when we then work out our sample concentration. Okay, so an additional problem that we might have is that when we put a real sample in our mass spectrometer or other instrument that we're using to measure, it might not behave exactly as our series of standards does. So that standards here are represented by these blue dots. But if we put in a sample that, say, had a concentration something like this, we might not get as much signal as we might expect. So it should plot up here, but it looks like we're getting less signal than we should do. Okay, and the reason for this is that some samples have lots of other stuff in them other than the elements we're interested in. So for instance, seawater, if we're trying to measure iron or cadmium or something that's got a very low concentration in seawater, that might be inhibited by the large concentrations of sodium, chlorine, potassium that are in that sample. Okay, so all these other ions that are in the sample might mean that we actually get a reduced signal. So we might reduce the ionization efficiency, we might reduce the sample uptake rate. So that leads to this problem that if we were to then, for instance, for this sample here, okay, if we were to actually go across and look at what intensity that gave us, okay, and use the calibration curve, we'd end up with a concentration that's over here, where its true concentration is over here. So there's a way around this problem, okay, and then the way around this problem is we use internal standardization, and this is a really commonly used technique in geochemical analysis, and that's rather, instead of looking at the intensity of the signal that we get for each element or isotope we're interested in measuring, we put in another element into our sample and into our standards. Okay, so for instance, we choose an element that is not geochemically interesting, so we don't actually want to measure this element, but it's easy to measure analytically, so it doesn't have any interfering other isotopes or other elemental interferences. We'll come on to that later. And we add, say for instance, we add 10 parts per billion of indium-115 to all samples and standard solutions. So we've added the same amount of this element to all of our samples and standards, and in a concentration that's much higher than we would expect to have for that element in the samples. So this means that what we can do then is, instead of measuring the intensity, we measure the ratio of intensities here. Okay, so we measure the ratio of the element we're interested in divided by the internal standard intensity. And the beauty of this is that if these samples did have their signal suppressed by having a high total dissolved solids or something that's meaning that the mass spectrometer is less efficient for those samples, it will also be less efficient for the internal standard. Okay, so this kind of corrects for the inefficiency of samples versus standards. Okay, so we then produce a calibration curve that's based on concentration and ratio of element of interest to the internal standard rather than just the intensity. Okay, so moving on now and thinking a little bit about some of the reasons why we might get this suppression or different efficiencies for different isotopes, different elements, is that particularly with some mass spectrometers like inductively coupled plasma sources, so this is a schematic of one of the machines that we have downstairs in the Grant Institute, is that if you have, say, 100% of your sample to start off with, by the time it gets into the mass spectrometer, so it goes through these cones with a small hole in, you lose quite a high percentage of the sample. So only a small percentage actually makes it all the way around to the collectors. And it turns out that the amount that gets around to the collectors is actually dependent on not only the element of interest, but also its isotopes. So it turns out that heavier isotopes actually get around this mass spectrometer a lot easier than lighter isotopes, which creates a problem. So this is an example for lithium isotopes. So the natural abundance of lithium isotopes has two isotopes, lithium-7 and lithium-6. You can see those have a natural ratio of about 12. But if we were to measure those on a mass spectrometer, we would get a ratio that's much higher. So we've preferentially fractionated the heavier isotope because that can make it around the mass spectrometer a lot easier. Okay, and this is a big problem for light isotopes like lithium because there's a large relative mass difference between 6 and 7. But even up at heavy isotopes like uranium, where we might be looking at uranium-235 and 238, there's a small difference in those masses, and even at these high masses, it can cause an error in the isotope ratio. Okay. In fact, this was one of the ways that fractionating using a mass spectrometer to fractionate uranium isotopes was one of the first ways that was tried out for enriching uranium for making atomic weapons. Okay, so it's possible to induce quite large isotope fractionations using mass spectrometers. So how do we correct for this this problem with the isotope ratio we measure is not the same as the sample isotope ratio? So we can use an internal standard, so we can add to our samples an isotope ratio that we actually know, or we can use naturally occurring isotope ratios that we know, and then measure the isotope ratios that vary and correct the isotope fractionation using the known isotope ratio. Or we can use this approach using an external standard, which is sometimes called standard sample bracketing. Okay, we'll just go through that example of that. So this is an example of standard sample bracketing. So over time, so this should be lithium-7 divided by lithium-6. That's an error. And a typical analysis time over here might be hours rather than seconds. Over time, we might measure a bunch of different samples, and we might measure a bunch of different isotope ratios, and they don't really kind of mean anything because they're largely fractionated from the true isotope ratio. We might want to say that this isotope ratio is maybe higher than this one's lower than this one, but we couldn't say much else. So what we do is, in between each sample measurement, we have a measurement of a standard. Okay, and the standard we know is the same as all of the other standards because it's a single kind of pot of solution of dissolved lithium, so it can only have one true value. Okay, and we can see that over time the fractionation of this standard in the mass spectrometer changes. Okay, so it goes up and then it comes down. Okay, it's a little bit noisy, but from this that we can see that it changes through time, but we can then use the difference between the average sample measurement, the average standard measurement, and each standard either side of that, each sample between those standards, we can use that to correct for the instrumental isotope fractionation. We do that with this equation here. We have the ratio measured in the sample divided by basically relative to the ratio measured in the standards. Okay, and we have this 1,000 in here because isotope ratio variation is actually quite small in samples. We can see now that we've corrected that, we now have converted our isotope ratios rather than absolute ratios into relative ratios, okay, which are quite commonly used in the geosciences, okay, rather than the absolute numbers. And we can see that we can now show that this sample indeed was higher than this sample, which was lower than this sample, and so on. Okay, we can take this a little bit further and look at the standards. So rather than just getting rid of these standards we've used to correct, we can actually look at each standard in turn and how that is different from the standards either side of it. Okay, and that variability through time is essentially how precisely the mass spectrometer can make a repeated measurement. Okay, so if you measure the same thing over and over and over again, what is the variability in that measurement? And we can measure the standard deviation of that and give 2 standard deviations, which is approximate, so kind of the 95% confidence interval. Okay, and we can then start to use that to work out how precise our measurements are. So this is quite often termed the internal reproducibility of the mass spectrometric method. You can do the same thing by repeatedly measuring a sample over and over again. Okay, and you get a similar kind of 0.4, in this case, per mil isotope ratio variability. Okay, so we can use multiple replicates to assess our precision. Okay, so moving on to other things that can go wrong. So this is some examples using strontium isotopes, and strontium is quite often used in the geosciences. It can tell us about kind of where various contributions of continental versus oceanic sources to ocean chemistry, and this is kind of a record of ocean chemistry through time, which is a proxy for mid-ocean ridge spreading rate, or it's a proxy for weathering, however you look at it. You can also use strontium isotopes are used for provenancing work, so working out where things have come from. So this is a Neanderthal tooth, and from this you can kind of work out that different strontium isotopes during different times of growth of this particular individual show that he's kind of living in different places throughout its life. Okay, which is kind of quite interesting. So these are the isotopes of strontium. There's a minor isotope 84, there's an isotope 86, 87, and 88. Okay, so we might particularly be wanting to be interested in the 87 to 86 ratio, because this is the one that varies the most in nature. Okay, there's relatively little variation in the other isotopes. Okay, so the first thing is that if the true sample isotope measurements are in blue here, okay, what we would measure, if we could measure just the strontium, would be the kind of the orange, because we have this slight preference for the heavy isotope. Okay, but because we know that the 88 to 86 ratio is kind of near constant in nature, we can use that, okay, the measured value in that, to correct for this additional isotope fractionation. So we've got the measured ratio is the true ratio times the mass difference between basically the ratio of the masses, so the 88 over 86, to the power of some fractionation factor. Okay, and we can use things like that to kind of like work out the true isotope ratio. Okay, the details of that are not important. We can just, the concept is that if we know an isotope ratio, we can measure it, and the difference between the known ratio and the measured ratio tells us the isotope fractionation, which we can correct for. Okay, but there are not just kind of fractionation problems, there are also other problems when we do mass spectrometry. Because when we measure mass spectrometry, the mass spectrometer only separates out elements according to their mass to charge ratio. Okay, so strontium would kind of look like this, but there might be other elements in our mass spectrometer or in our sample that cause there to be isobaric, so isobaric meaning essentially the same weight, same mass, elemental interferences. So for instance, if we were just interested in the 86 to 87 ratio, the 87 beam would comprise strontium, but would also include if there was any rubidium in the sample or any krypton, which is a gas, which is unfortunately in the atmosphere. So if we're using a inductively coupled plasma mass spectrometer, there would always be some krypton in our sample because it's open to the atmosphere. Okay, so we need to somehow deal with this problem. In addition to things that are the same weight, we also have this problem that some that are elements that are maybe twice as heavy, if they end up being doubly charged, so having a 2+ charge on them, they will also interfere. So in this case, turbulent. And then again, we can form molecules in our mass spectrometer, maybe oxides, hydrides, nitrates. These can also interfere if they have the same mass. Okay, so if we try to measure, for instance, the 86-87 ratio using the 88-86 ratio to correct for, we'd have all these extra masses on top of here, which would be completely ruining our measurement. So we need to get rid of them, okay? And the first thing we can do is we can do some chemistry on our sample. So we dissolve up our sample, and then we just chemically remove all of the elements that are not strontium from our sample, and that should hopefully remove these mass interferences. Okay, and the way we do that is using this chromatography method, where we kind of dissolve up our sample, we put it on the top of a column like this, and in this kind of like column here, we have some sand with some kind of special organic geochemistry coating, which is kind of essentially magic. That preferentially grabs on to different elements depending on which acid you're dripping through, and then over time, different elements represented by different colors here can drop out of the bottom of the column, so we can separate out the strontium from the things that we don't want to be in our sample. The next problem would be the krypton, which we can't separate out chemically in that way because it's a gas and it's introduced into our sample when we put it into the mass spectrometer. So we could use a type of mass spectrometer that doesn't have a connection with the atmosphere. So we could use a thermal ionization mass spectrometer, which is kind of the sample goes in and then we pump out the atmosphere. So that would remove the krypton. Okay, that would have a disadvantage that we would only be able to measure a few samples a day, perhaps, but we would get better data, we would get higher precision data, and we wouldn't have to worry about this krypton interference. Another thing we could do, rather than actually getting rid of the interference, is just measure it. Okay, so we have other isotopes of krypton, 85, 83, and 82. Okay, and they're kind of, they don't have any other interferences on them. So if we measure these, okay, and we know the ratio of this isotope to this isotope in the gas, which we could again determine by measuring a sample that didn't have any strontium in, we just measure the krypton, we can then mathematically work out how big this interference is on the 87. Okay, so that's another way that we can get around these problems. We can do maths, which is you know, mathsy. Okay, so those are mass spectrometry type problems, but we also need to think about what we're doing to the sample before it goes into the mass spectrometer. So quite a lot of geological samples are not really suitable for putting straight into an analytical instrument. Sometimes they are, but quite often they are not. So for instance, for gaseous samples, we might in fact be able to directly kind of like, for instance, sample some water from a well, okay, and then we could just put that water sample in a glass vessel, evacuate the vessel, and then the gases will kind of equilibrate between the headspace in the vessel and the dissolved gas in the liquid, and we could then just put that gas directly into the mass spectrometer. I mean, that's a thing that we could do. But for other things, we might have a very low concentration of gas, so we might have to absorb it onto the surface of some kind of like solid material. So for instance, for measuring mercury gases, it's quite often to absorb mercury out of a large volume of gas onto a gold basically filaments or some gold wool, and that concentrates the gas on the surface of the gold, and then when you want to measure it, then you heat up the gold into a smaller volume of gas, and that basically the mercury desorbs off, and then we can measure a higher concentration into the mass spectrometer. Okay, but for some samples like solids, we might need to, if we've got say a rock, we might need to dissolve that rock, or we might need to we might be interested in doing an acid leach for certain minerals out of that rock, or we might be interested in doing something to that rock to make it give off gases, either just heating it up or dissolving it in acid to evolve CO2. Okay, so those are things that we might want to do to it to get something to go into the mass spectrometer. For liquid samples, so seawater, we might find that the element we're interested in measuring is far too low a concentration to measure. Okay, so we might think, well, we've got to concentrate that sample. We've got to remove a lot of the water and a lot of the salts out of that. So we might do some chemical extraction. Now, the problem if we do any of these things is that anything that we do to the sample, okay, we might lose some of the element we're interested in. Okay, and if we lose some of the element we're interested in, then our final concentration will be too low. Okay, so it's very important to keep track of the efficiency of all of the chemical processes that you do to your sample before you analyze it. And this is quite often referred to as yields of these kind of experiments, yields of the things that we do. So this is kind of an example. So we might have some sample, like a water sample that has some kind of element that we're interested in. Let's say that this is iron, for instance. So there might be some atoms of iron that are dissolved in our water, and that's what this is represented over here. Okay, but they're too low a concentration. They're below our limit of quantification on our mass spectrometer, let's say. So what we want to do is we want to get those atoms into a smaller volume of liquid. Okay, and one way of doing that is a liquid-liquid extraction. So we could add an organic solvent, maybe isopropyl ether, and add that to the water. It won't mix with the water because it's immiscible. But if we kind of like shake it up a little bit and kind of force there to be a very high surface area, there's a partitioning of the iron between. Some of it wants to be in the water, but most of it will want to be in the isopropyl ether because its iron turns out more soluble in the isopropyl ether than the water. So we can basically pre-concentrate the sample that way. We then just siphon off the organic solvent, and that gives us a higher concentration of iron in our sample. But you can see that this wasn't 100% efficient. So some of the iron did get left behind. Now this is kind of 50% might be an extreme case here, but if we then made a measurement of that and we tried to back calculate the original concentration in the water, we'd be 50% out, which is a lot. So what we need ways of figuring out what this yield efficiency is. So one way is to do that extraction again. Okay, so if we re-perform that extraction on the now depleted water sample, this proportion of into the organic phase in the water should be the same because the chemistry is the same. So that if we then measure the first extraction and the second extraction, the ratio between them, okay, should give us the percentage efficiency. So imagine if it was 100% efficient, then there would be all of the iron in this fraction and none in this fraction. Okay, so it gives you the efficiency of the extraction. Another way is a technique that's quite common in geology or in earth sciences more widely is isotope dilution. So in this case, we add an isotope that either doesn't occur in nature or is wildly fractionatedly different from the natural isotopes of iron. We add a known amount of that to our sample. Okay, so that means that there's now more iron in the dissolved in the water, but there is some difference. So this brown dots represent the basically the tracer isotope, or sometimes called the spike isotope. So this is a know exactly how many grams of that or how many nanograms of that we've added. Okay, then we do our extraction again. Okay, and then we have some extracted iron at the end that's got a high concentration, so we can measure it, and it now has both the naturally occurring and the spike or tracer isotope. And the key thing here is that this efficiency of extraction from the water into the organic phase here is the same for both the tracer isotope and the naturally occurring isotope because they behave chemically the same. So we can then, rather than try and work out the amount, we just measure the ratio of the naturally occurring isotope to the tracer isotope. That's the only thing we measure. And then we know the amount that we added at the beginning. Okay, so you just times those two things together, and that then gives you the amount of naturally occurring iron or whatever element you're interested in at the beginning. Okay, so that's isotope dilution. Okay, and it's a very, very accurate way of making sure that your yields are determined. Okay, another issue that's quite prevalent in quite a lot of types of mass spectrometry is the memory or background. So this is the case where we, for instance, just move on. So if we've got time along the bottom, we might put a sample into our mass spectrometer, okay, and then the signal will increase, and then we might measure it for a bit as it's kind of sucking up the sample, or the sample kind of being ionized in the gas chamber or something like that, and then we stop measuring our sample, and over time the signal gradually declines. Okay, and it goes back to somewhere near where it started. Okay, we never go back to zero because we always have some background noise in our system. So the problem is that if we then measure the second sample immediately afterwards, we'd have this issue that we basically get too much signal because we haven't got rid of all of the sample before we started measuring the next sample. Okay, so one thing that we could do is just measure for longer or wait for longer before we measure the next sample. Okay, or more intelligently, it would be a good idea to actually measure the background signal just before we have our sample go in, and then when we're actually measuring our sample when it's up to its maximum intensity, and that is actually the signal that we're measuring. Okay, because it's important to measure that quite often the difference between the measured signal is not all the way down to zero, it's down to some background level. Okay, and that can either be due to memory still washing out, or it could be due to the inherent background noise in the instrument. Okay, so it's important to measure both when we've got a sample in, but also measure when we don't have a sample in, so we have something to compare our peak heights to. So kind of to summarize some of the things that we have to do to correct our data. So ideally, we'd make some kind of concentration calibration where we produce a calibration curve that looks something like this, where we know kind of the concentration of some standards, and then we can measure unknowns for their signal, and then use that to work out what the concentration is. But there are problems with that if we have interfering elements, so things that add to the signal from different elements, or molecular interference, or these double charge interferences. For any one concentration, we'll end up with more signal than we should have. Okay, and if we have matrix problems, so this is basically lots of other stuff that's in our sample, okay, that's inhibiting ionization or slowing sample uptake, that tends to reduce this curve, and quite unpredictably. Okay, now we can. So this is this effect here. So we can try and get rid of that effect using the internal standardization mentioned earlier. But one of the problems with that is that it does make an assumption, and that assumption is that this signal suppression, due to having other stuff in the sample, is the same for all elements. Okay, so it's the same for the element you're interested in and the internal standard element. Now that's not always the case. Okay, so we have this final method to try and solve that problem, and this is a method called standard addition, and this is kind of quite counterintuitive, but I'll just talk you through it. So we take our sample and we split it into something like 5 equal parts. Okay, and we measure out those 5 equal parts very, very accurately. And then to the first one, we don't do anything. Okay, so that's still just our sample, but a fifth of it. And then to the next one, quite counterintuitively, we add a known amount of the element that we're interested in measuring. Okay, so if we're trying to measure iron, for instance, we add a small amount of iron to our sample. And to the next one, we add a little bit more iron. And to the fourth one, a bit more iron. And to the fifth one, a bit more iron, which is kind of a little bit counterintuitive because we've just contaminated these 4 samples here, 4 aliquots of our original sample, sorry. We've just contaminated those with the thing that we're trying to measure. But the important thing is that we know exactly how much we've added. Okay, we would then make them up all into the same volume, dilute them, ready to run on the mass spectrometer. So we now know that this one should have more concentration than this one, sorry, less concentration than this one. This one should have more concentration of this one, because we know that we've added more of that element in. So this is what we get. So if we were to measure those, we would get this is our one that we sample that we haven't added anything to, and we'll get some signal for that. Okay, we don't know how much that is due to signal suppression because of there being other elements in that sample. But then for these other guys, okay, these should give higher signals because we've added a known amount of the element we're interested in this case, maybe iron, to that sample. So we've added a little bit to this one, and we've added a little bit to this one, we've added a lot more to this one, we've added loads to this one. So this actually gives us a calibration curve, okay, that is specific to this sample, in that these can be considered as standards, okay, and this is our sample, and the standards are exactly the same. So they have exactly the same matrix, so they have exactly the same total dissolved salts in them. They have everything is identical. So that means that if, for instance, there was a high concentration of total dissolved salts, something suppressing the signal, that signal suppression as a percentage will be the same for all of these sample aliquots. Okay, so that means we will still get this straight line. Okay, and as it turns out, the intercept with the x-axis gives us the concentration of our sample that we haven't added anything to. Okay, so it basically acts as a matrix independent calibration curve, which is great because it means we get a very, very accurate measure of the sample concentration. But one of the problems is that we have to measure one sample 5 times to get one measurement. So and we have to do all of that chemistry beforehand, adding in very carefully known amounts of the elements we're interested in. Okay, so it's much more sample, much more labor intensive, okay, much longer analysis time, but we do get a very, very accurate result. Okay, so just to finish off, I'm gonna just quickly, there are these things that I guess I don't really want to talk about so much: detector background noise or abundant sensitivity. And you can look those up if you really want to. But the thing I want to talk about briefly is blanks, and then reproducibility and accuracy. Okay, so we've really talked already a little bit about reproducibility. So that's, you know, if we measure one sample repeatedly many times, okay, how do we how good are we at getting the same number over again? Okay, so that's a measurement of the precision. Okay, but talk a little bit about blanks now. So if we wanted to measure, say, a rock down here, measure the amount of lead in that rock, for instance, that might be something that might be geochemically interesting to us. We'd have to dissolve that rock. Okay, perhaps if we wanted to introduce it into a mass spectrometer, we'd have to do lots of drying down and chemical separations if we wanted to, for instance, measure it by thermal ionization. Okay, if we wanted to measure it by plasma ionization, we might just dissolve it up in acid. But every processing step we do on the way has the potential to add lead to our sample. Okay, so we dissolve it, we add acid. There might be a little bit of acid already in the, a little bit of lead, sorry, already in the acid. There might be some dust in the lab that we do our sample processing in. Okay, we might do some chemical separations to purify the lead to put it onto a thermal ionization filament. That processing might add some extra lead to the sample, and even distilled water might have a small amount of lead in when we dilute our samples up. Okay, now all of this will contribute to the lead that we measure. Okay, but we only want the lead that's in the rock. So what we have to do is we make this measurement of the total lead, so lead from our rock and from all our sample processing, and then we have to make a separate measurement. So this is quite often referred to as a total procedural blank, where we do the total procedure. We get this thing down here, which is a pretend rock. So we imagine that a rock exists, and we do everything to that imaginary rock that we would to a sample. So we dissolve it, we put it in a lab, we do some processing, we might dilute it up. And we might even do this more than once. We might do this a number of times to get an idea of the variability or get the mean blank value. And then we just subtract that measurement from the measurement of when we do it with samples. Okay, so that's how we correct for blanks. And then kind of lastly, we need to think a little bit about precision and accuracy. Okay, so we mentioned precision, and that's basically your ability to measure the same thing over and over and over again, and get the same kind of result. And that could be either if you measure the standard solution on the mass spectrometer and you repeat that many times, you could think of that as that's the reproducibility of your mass spectrometer. If you had to do some sample processing, you might get one sample and split that into many parts and do sample processing on that number of times. That might give you another measure of precision that includes all of the errors that you might introduce when you make mistakes in the lab. But that's, I guess if you have a good thing to do is to be precise, okay, but also to get the right number. Okay. Sometimes it's okay to be imprecise, in fact. So if the question that you're asking geologically has a huge variance in concentration or isotope ratio, will give you the answer to that problem. It's okay to have an imprecise measurement, okay, especially if it's a lot cheaper and quicker, as long as it's accurate, okay, as long as your measurements kind of overlap with what you expect the real value to be. Okay, what's really bad is if we start to not get the right number for something, Okay, even if we're really precise, we might be precise but wrong. Okay, this is definitely bad because we end up making incorrect conclusions when we start doing this. So how do we check that we're getting the right number? So one of the things that we can do is use reference materials. So when we're making our measurements, we'll have a set of standards, which will usually be a set of solutions of known concentrations, which we might have certified, or we might actually have made up ourselves by weighing out a known amount of iron metal or cadmium metal or some gravimetrically determined internationally recognized standard kind of metal. But we might also want to use these things called reference materials. So these are essentially samples that are distributed to geochemical labs around the world, and they should all have the same value, and they should all have compositions that are similar to the kinds of samples that you're measuring. So if you were measuring basalts, you might get a standard of the Hawaiian basalt, okay, which is produced by the Hawaiian Volcano Observatory, which is like Basalt Hawaiian Volcano Observatory, and this is the second one that they produced. This is the first one they were produced. And this is basically just a lump of basalt from outside the door of the Hawaiian Volcano Observatory, and they've ground it up into a powder to make sure it's really, really well mixed. So every little pot should be geochemically the same. And these have been measured by a whole bunch of different labs around the world. And there are agreed values for the concentration of different elements, of different isotope ratios. So you would measure these along with your samples, okay? And then you would check that you're getting the right number. And when you report your results, you'll also report the ratios or the concentrations that you get for these standards. So people from other labs, when they see your data file, they can see that you're getting good quality data. Okay, so I'm going to stop that, go back to, oh, it's me again. Okay, so hopefully these 3 videos have given you an introduction to the kinds of things that matter for mass spectrometry and geochemistry more generally. You have an idea of what mass spectrometers are, what types there are, and I think most importantly is this last video about the things that you need to worry about when you're dealing with this kind of data is plural, these kind of geochemical data. Okay, so if you haven't kind of grasped all the things in the videos, go back through the videos, make some notes. If you're still unsure, post things on the discussion forum, which I will endeavor to respond to. Okay, so that's the end of this, and then hopefully we'll find this useful in the tutorial workshop thing on Tuesday. Okay, right. How do I stop?